In this video, we're going to look at linear regression, a technique used to determine the relationship between two or more variables. What we're going to do is to open up a built-in data frame in R called trees. So the trees data frame now appears up in my global environment. And let's ask, how big is this data frame? It's a dimension command, and we can see there are 31 rows. Each of those corresponds to a different tree, and there are 3 different variables associated with each tree. Take a look at the first few rows of the data frame using the head command, and we see we have girth, height, and volume for each of those 31 trees. Now, to measure the volume of a tree is very difficult, but to measure the girth of a tree is easy. And what we might like to know is, can we measure accurately the volume of a tree by simply measuring the girth? Is there a relationship between girth and volume? So what we're going to be doing is using girth as our predictor variable or our x variable, and we're going to use volume as the response variable or the y variable. And to do a linear regression, we just call the function LM, that stands for linear model. And what we do is to first give the response variable. So I need to give the data frame and then the particular column that I'm interested in. So in this case, it's volume. Then I add the tilde, and then trees girth. And I run this single line of code, and I get some output down in the console. What you can see are 2 coefficients. One of them is the y-intercept, which is equal to about minus 36, 37, and the second is the slope, which is 5.066. So to estimate the volume of a tree, what I can do is to measure the girth, multiply that by the slope, 5.066, and then add to it the y-intercept. In this case, the y-intercept is a negative number, so I'd be essentially subtracting that value from the product of the slope and the girth. What we don't know from the limited output below is whether or not this is even a statistically significant relationship. What we need to do is to save our whole summary as an R object. So I'm going to call it mod1, model 1, and you can see that mod 1 has now appeared up in my values list up here in the global environment. Now what I can do is to call summary on mod 1, and now I get a whole lot more information about my regression. I still get the formula that I had in the limited output above here, but now I've got some information on the residuals. The residuals are the difference between the predicted value and the observed value. And for a good regression, you would like to see the median residual being pretty close to 0, a good fit, and you'd also like to see some symmetry. So this is the first quartile and this is the third quartile, and the absolute values should be pretty similar to each other, and they are. Similarly, the minimum and maximum should be about the same magnitude, and they are as well. We can also see some statistical analysis of the intercept and the slope. We don't normally test the intercept, whether it's different from 0 or not. We're usually much more interested in the slope. So what we can see here is that our p-value is vanishingly small. In other words, the chances that such a relationship as we observed arising by chance is much, much less than p less than 0.05. And you can see that 3 asterisks are indicated here, which indicates it's significant at below the 0.001 level. So we can feel pretty good that there is a significant relationship between girth and volume. We can also note a little further down there is another statistic called multiple R squared. R squared is a very useful statistic because it tells us how good a predictor our predictor variable is. R square can vary between 0 and 1. If you have 2 variables that are totally unrelated, then your R squared is going to be equal to 0. if you can predict exactly your response variable based on the predictor variable, then your multiple r squared would be 1. And here we can see that our r squared is pretty close to 1. So we actually have a very powerful relationship here, that almost 94% of the variation in volume can be explained just by knowing the girth of the tree. And we can also see we end with an F statistic, and it turns out that this test is related to the test up here of the slope, and you can see in fact that the p-values are exactly the same. There are other attributes we can look at from our analysis, because I've saved the whole analysis as an object, so I can look for other attributes of mod 1, and you can see there are various and sundry other aspects of the analysis that we could look at, like the fitted values and the residuals and the coefficients and so forth. So if we were interested in seeing, for instance, the fitted values, all we need to do is to type fitted values and call our object mod 1, and there we see the 31 different fitted values for our regression. Now it turns out that when you do a linear regression, there are two important assumptions that are made, and one of them is that the residuals should be randomly distributed. Another way of saying that a statistician might use is to say we have homogeneity of variance. And it turns out that R has an easy way for you to assess the likelihood of these assumptions being met in a graphical manner. So what I'm going to do is just to go down to my console. I find this particular command easier to run from the console, and I'm just going to say plot mod 1. And I get a plot here of the residuals, that is the difference between the observed and the predicted, against the absolute value or the value of the fitted values in our regression. Ideally, what you want to see when you look at a plot like this is the night sky. In other words, you want to see a whole bunch of stars that are just randomly distributed over the entire plane that you're looking at. And this is pretty good. We don't really have a preponderance of high or low values at one end of the x-axis or the other. So we can feel pretty good that we have homogeneity of variance in our particular plot here. The second assumption is that the residuals should be normally distributed. So we expect most of the residuals to be pretty close to 0, and then we want to have a symmetrical distribution of the more extreme residuals to the left and right of that median 0 value. So what we expect to see is a bell-shaped curve. Well, what we can do is to look at that using a QQ plot. And we can see there are 31 points on this plot, and there's also a faint dotted line there. If the residuals are normally distributed, then all of these points should fall on or pretty close to that line. And we can see that there are a few that are below, but by and large, this is a pretty good fit. So we can feel pretty good that the assumption of normality of the residuals is met here as well. I'm going to go through the next two plots to get out of this particular function, and these are plots that we won't examine in this video. They can be used to drill down even more on the quality of one's regression. So what we're going to do is to go back up here, and we can plot our data. So I'm going to use what's called the base R graphics. So we just say plot trees, and we'll give the x value first. So that's girth and trees volume. And it should appear in our lower right panel there. And we can also add the regression line. Since I have that embodied in my mod 1 object, I can just call that the AB line function, and there's my regression line. So you can see from this plot that the regression is pretty good, as you would expect with such a high R-square value. A few points are a little bit off the line, but by and large this is a very good regression.